So my name is S.Tarr, and I was asked to come here and talk to you today about silicate hardeners, silicate densifiers. I wrote an article back in 2014 with the same title, A Condensed Look at Liquid Surface Densifiers. And first thing I want to say is that I'm not anti-silicates in any way. They perform a service, and I like them. I use them on almost all of my industrial slab projects. Owners want them. They serve a purpose. But let me just give you a little background on what the article was about. So back in 2014, Concrete Construction Magazine was about to publish an article submitted by an author called A Hard Look at Liquid Surface Hardeners. And in this article, the author claimed that the silicate hardeners made no improvement to the wear resistance. He used a Chaplin abrasion tester, went out and tested surfaces that were treated and surfaces that weren't treated by these liquid surface hardeners, and he wasn't finding any measurable difference between the two. So the editor of Concrete Construction Magazine called me and he said, do you like silicates? Yes, I use them almost all of my projects, and well, we're about to publish this, it's going to be a bomb. Would you please publish an article that's pro silicates? So a hard look at liquid surface hardeners. I loved the choice of words there, so that's where A Condensed Look at Liquid Surface Densifiers went into the same magazine. And I said, I will definitely give the pros, as long as I can also give the cons. Can I talk about what surface densifiers do, densifiers hardeners, and what they don't do? And he said, sure, absolutely do that. So just in a nutshell, what do they do? So we know that the silicate in these silicate densifiers, you have sodium silicate, potassium silicate, magnesium fluorosilicate, lithium silicate, a bunch of different types of silicate. It's the silicate that we like. It's a bunch of different other media that get that to you. What does it do? The silicate reacts with available calcium hydroxide in the surface of the slab to convert that to calcium silicate hydrate. So as we know, when you cure concrete, you get two components: calcium silicate hydrate, that's your strength developing, your durability developing, and calcium hydroxide is kind of a byproduct. So the silicates convert calcium hydroxide to calcium silicate hydrate. Sounds like a good idea. So because it does that reaction, it occurs in the surface pores of the concrete, and because it occurs in those surface pores, technically there is a hardening or a densifying that takes place. They are called hardeners and densifiers, and that's what they do. We spray them onto surfaces of concrete floors, and as we polish those floors and scrub those floors over time, they become shiny, easily cleaned, all the properties that owners want. Most owners that I work for absolutely want these properties, and they ask for them, and we always use them. All right, what don't they do? Well, how much reaction occurs? It depends. It depends on how much calcium hydroxide is available, right? So the more calcium hydroxide there is when you apply the silicate, the more reaction you'll be able to get. If there's no calcium hydroxide available, then no reaction takes place, and there's no benefit. But there's some calcium hydroxide, we count on that, right? So, but the better the curing, the more calcium hydroxide you have. The more calcium silicate hydrate you have, because that's what curing does, it develops these two components. So the better that initial curing, the more calcium hydroxide we have. So we want to cure that slab, and then we definitely want to harden that slab. All right. What else reacts with calcium hydroxide? Pozzolans react with calcium hydroxide, right? Or fly ashes, or silica fumes, or slag. That reacts with calcium hydroxide. And so does carbon dioxide. Carbonation is a reaction we just heard about a minute ago. Carbon dioxide from the air reacts with calcium hydroxide in the surface of the concrete to carbonate the surface of the concrete. And we'll talk a little bit about that, but the point I'm making is there's other things that also struggle for reacting with that calcium hydroxide. Silicate's not the only thing. So you need to know, are there other factors that I need to consider? How effective is putting a silicate down going to be? Are these materials curing compounds? Do they cure concrete? And I'll show some slides on that. I don't believe that I've ever seen that they actually serve as a curing compound, right? Also, moisture vapor mitigation, we heard a little bit about that. There was a question about it. Oftentimes, there's an office area, putting down a floor covering, and if it's a moisture-sensitive adhesive, we have vapor emissions and vapor transmission. Are these products, they've been marketed, some of them, as being moisture vapor mitigation products. We have a moisture vapor issue. Can we spray down a silicate and will that take care of the problem? So I'll address these. This is what we're looking for, and certainly this is a slab that was well cured, it was well finished, well cured, and it was hardened and densified, putting down a silicate product. And this owner, very thrilled with it. One of our distributors, our e-commerce distributors. So how do we put these down? They're topically applied. There is some components that are integral, so they're admixtures. You can get a silicate admixture, put that in the concrete, and I'll talk a little bit about that. But for the most part, they're topically applied, the ones I want to talk about today. And you put them down. Depends on the reaction process. So the sodium silicates, the potassium silicates, the magnesium fluorosilicates, the way that they work is they're flooded onto the surface and you scrub them around for about 20-25 minutes. They react with that calcium hydroxide. They form a white gel. And when that white gel forms, very important to get that off there. The reaction is complete. Flush it with water and vacuum it off. So this is kind of the process. There's a gentleman applying it. Here's what's typically done in a large industrial manufacturing facility. Before anything's in there, you use scrubbers to put it down. You put it down with scrubbers, scrub it around for 25 minutes, add water, and vacuum it off with your scrubbers. Zamboni type, tenant type scrubbers. All right, here we are. Usually it's bay by bay. And that's how those types are applied. Again, those are the sodiums, potassiums, magnesium fluorosilicates. All right. Now, some of these projects are really fast track. When I go for my last final walkthrough of some of these projects, there's semi-tractor trailer trucks lined up. They are ready to move in. They're right on the heels of the contractor. We know that. These turnaround times on these projects are really, really short. So is there any way that we can shorten the schedule or ease up on the schedule? Because it's difficult to get an open facility with nothing in it. No racking, no product, totally open. Take your time. Go treat it with your silicate. We got lots of time here. There's never that time, rarely that time. So one of the things that's been done over the last few years, maybe a decade or so, is can we put the silicate down right after final finish, then cure it, and will that product then eventually do the same thing as putting it down 28 days later or sometime later to react with the surface? So we can do that, as it turns out. We found that that's a very effective way of doing it. Here's a project. You can see the finisher finishing, and he'll usually signal the silicate applicators, and they come in right after. So he's still finishing there on the right, and there they are coming out right away to spray on the product. Any of these products can be applied at this time. I don't want to say that you can't, but lithium silicates, I didn't mention those before, lithium silicates don't have to be scrubbed around for 25 minutes. They don't form that white gel. You don't have to flush it. You don't have to pull it off. Lithium silicates are applied at a very low concentration, and you walk away. So for this particular application, lithium silicates just fit right in. You apply them down to the surface right after final finish. You can see these gentlemen doing this. You can see them finishing right back. The finisher will usually signal. We have a pre-construction meeting just to make sure we're all on the same page. Last finisher needs to signal. These guys get on and they apply the silicate product to it. What else is happening at that time? Floor flatness and levelness testing. We've always got that guy ready to go. Joint saw cutting. We never want to delay joint saw cutting. So there's a lot going on. Pre-construction meeting, very important. Let's get on the same page. A lot going to be happening here right after that final finish. We cannot delay joint saw cutting. So again, putting down a lithium silicate where you don't need to wait that 20-25 minutes kind of falls in my opinion. But not to be said that you can't do a sodium silicate or potassium silicate. But this is what we've seen and we like this process. All right, after that is done, you put down a curing compound. Some form of curing because we want to lock that moisture in, and I'm going to talk about curing a little bit here. Underneath that curing compound, this is a dissipating one. Underneath that is our silicate product. It reacts with the slab surface during the curing period. Afterward, we clean off the curing compound that had dissipated, and we scrub the floor and buff it up, and it shines. Beautiful. There's no need to put down a silicate later. A lot of times we'll put down what they call a spiff coat. I have nothing against putting down another coating of it, but it all depends on how much calcium hydroxide is still left in the slab surface. If there's nothing there because we've already reacted with it, then that spiff coat won't have a lot of effect. All right, so just another view of a dissipating curing compound. What's a dissipating curing compound? It breaks down under ultraviolet light. So sunlight shines on it, we've got good exposure here, it breaks down a couple of weeks, and it cleans off relatively easily, right? That's the concept. It doesn't disappear, we still have to clean it off physically, but it breaks down and it's easier to clean off. So let's talk about what is curing. Can silicates be used as the curing compound? Do we need to put something down over the silicate, or can we just put a silicate down itself? So curing, just in our concrete terminology, says an action taken to maintain moisture and temperature conditions in a freshly placed cementitious mixture to allow hydraulic cement hydration and, if applicable, pozzolanic reactions to occur so that potential properties of the mixture may develop. That's what our concrete terminology says. And you know, when we do an industrial floor, what is the part of the floor that we really care most about? Is it the middle of the slab or the bottom of the slab? Of course, it's the exposed surface. So we want to cure and we want to develop the properties at the exposed surface. Properties we're looking for: abrasion resistance, wear resistance, ease of cleaning, of course, and all the other flatness and all that. But those are the main things right now. I've got a couple low wear resistance slides I'll show you. But again, we develop two things in this process: calcium silicate hydrate, that's the good stuff we want. Calcium hydroxide, it's just a byproduct, it doesn't make anything bad necessarily, but if we can react with that calcium hydroxide using a silicate, then we can change that back into more calcium silicate hydrates. But again, as I said, we've got pozzolans and carbon dioxide, so this is a race. Everybody's racing towards calcium hydroxide. What is adequate moisture and temperature? So if you look in the PCA documents and ACI 308 documents, there's a lot of different ranges of temperatures that we talk about, but there's general agreement that below about 80% relative humidity, hydration stops. It's too dry. You're not hydrating the cement portion. So, you know, take that with a grain of salt. It's something around 80%. Temperature, same thing. PCA and ACI both seem to agree. At about 40 degrees below that, we don't have enough temperature to adequately cure. So we need to keep that temperature above 40 degrees. As we look in our curing documents, 40 degrees is that magic number, and 80% relative humidity is enough moisture to hydrate the cement, cure the concrete, right? So that's what our documents are showing. We remember the days of applying water with sprinklers and soaker hoses under burlap or whatever method you like. Tremendous amount of additional water added to our concrete or our projects. This certainly cures the concrete, no problem. If that's your intent, you're going to achieve that by adding water and continuously flooding the surface. A lot of extra water going into your base, going into your project. What do you do with this extra water? I don't see that, thank goodness, anymore. We don't necessarily add water continuously for the curing period. It's about trapping the water. All concrete mixtures that we use for industrial slab mixes have twice as much water that the cement portion of that concrete mixture needs to hydrate. There's twice as much. And probably the most common thing that I do is try to optimize concrete mixtures. Everybody's looking at optimizing mixtures, lowering that shrinkage, lowering your cracking potential, curling. These are the things that are really important for industrial floor slabs. So I spend a lot of my time optimizing these mixes and reducing that paste content, reducing the water content as low as possible. But with those efforts, we still have about twice as much water as the cement needs. We still have plenty of water. A lot of that goes out in the bleed water, and we want to let that happen. But we still end up, after that concrete hardens, plenty of water that dries out over time. So it's about trapping that water. There's a simple technique of just putting polyethylene down. Now, we all know that when you pick the plastic up, there's a very good chance that you're going to have discoloration using this type of curing, because you get that greenhouse effect where the plastic is in contact with the concrete. You get one color. At each wrinkle, you get a different color. Very common to see that when you pick the plastic up, and just be aware that that's possible if that's not desired by the owner. You know, maybe this isn't the curing method, but certainly that will lock in the water that we have and hydrate and cure the concrete. There are other cure coverings out there available. Here's a very popular cure covering. This is a plant-based material, so it's a single use, but it absorbs a lot of water. So as you roll it out, if you're spraying it and you roll it out, it absorbs, it becomes heavy, and you can squeegee it very flat. So if color and discoloration is important, a product like this, if you're going to cover cure, is actually very effective. But locks in the water. No additional water is going to be added to this during the curing period. All right, curing compounds is another one. Curing compounds are very sought after, especially by contractors, because they have a construction schedule, right? They have to get this thing built. If you put down a cure cover, OSHA doesn't allow other trades to walk on that. It's slippery, trip hazards. To avoid all that, curing compounds are very attractive, very good option. So what does a curing compound need to do? It needs to do the same thing as any other curing method. We need to lock in the moisture. We're not going to add any to this project, but we're going to lock it in. There's plenty of moisture in that slab. We just need to keep it for a period of time, the curing period. So here we are, we're applying these curing compounds. All right, and they're applied to the surface, and we lock in the moisture so that it doesn't evaporate out of our slab. And we hydrate really the surface of the slab. Deep down into the slab, it takes a while for that moisture to migrate and evaporate out. Probably takes longer than the curing period for it to do that. I'm not too concerned about the properties of the concrete in the middle of the slab. It's all about the surface. It's all about the surface. Right, so let's talk about what is this minimum curing period. So PCA years and years ago did a curing study, you're probably familiar with it, but this is the results of it. You can see the curve. This is curing duration and percentage of 28-day strength. So if you look at that top curve, the solid line, moist cured the entire time. So it's 180 days. And you can see at 28 days, if you follow that up, you get 100% of your 28-day strength. You've cured it. You've kept it wet for the entire 28 days. At 28 days, you have the 28-day strength. Pretty simple. What if you take it out of the moist curing environment at 7 days? That's that next line down, the dotted line. Well, you don't quite meet the 28-day strength at 28 days. Hydration is kind of slowed down. You've taken it out of that full moist cure condition. But the interesting thing here is if you look, eventually you do meet the 28-day strength. You don't meet it at 28 days, but eventually you do. Somewhere down the line, 90 days, you get that 28-day strength. So that's kind of the basis of the recommendation of keeping the slab moist cured for a minimum of 7 days. That's kind of where that comes from. And we know there are people out there that are saying 5 days. Some people are saying 3 days. But here's some curves that show you what that curing period does and what the effect is on that 28-day strength that you're expecting. All right. We also know that as we hard trowel densify the slab surface, that becomes a very dense layer. We are vacuum dewatering that slab basically. We are compressing all of the water out of the top surface of that slab when we repeatedly trowel that slab. We used to call it burnishing. We're getting away from that term burnishing in most cases because the more glass-like we get that slab, back in the 90s everybody wanted a burnished slab, nice and glass-like, easy to clean. But the more glass-like we get that slab, if it's not in a temperature-controlled environment, that warm front comes in, your slab is slightly cooler than the dew point, and you condense liquid water from the air as you open your cross-dock doors. It basically acts as a dehumidifier, a giant dehumidifier for the city of Dallas. You've got all these things. So because of that, we call it slab sweating. Because of that, we don't burnish anymore. We still want a hard trowel, nice tight hard trowel, but we want it shy of burnished. We don't want it to be glass-like. But we're still densifying, troweling that surface. And as we do that, the moisture evaporation rate for the concrete below that is slow. We know that from our floor covering testing. We always test the concrete to see if it's acceptable moisture condition. There are tests to do that. You can drill into the slab and do a relative humidity test. You can perform, of course, calcium chloride test on the surface. But we know that that hard trowel surface delays drying substantially. It locks in the water. So no problem with that. The concrete below that hard trowel layer is going to cure. It's going to hydrate. You're going to get your full properties of that concrete. Again, it's all about the very top surface of the slab on top of the hard trowel layer. That's what we're really interested in when we talk about proactive curing. So what is a curing compound? Well, we have a couple of ASTMs that tell us what a curing compound is. One is ASTM C309. It's a standard specification for liquid membrane-forming compounds for curing concrete. That's the name of it. You go through the document, it has all these requirements on what a curing compound is. It references another standard test method, C156, which is the water retention by concrete curing materials. So how much does that curing material retain the water? That's what we're looking for. We're looking for it to keep the water in. So it's C309 says that when you use C156, we can't have a moisture loss any more than 0.55 kilograms per square meter in 72 hours. Now this ASTM C156 test is very aggressive. It is a high temperature, low relative humidity, has an evaporation rate, a constant airflow, very difficult. I'm looking at doing a study because I'd like to see different materials that are on the market, all of our very popular materials that we see time and time again submitted in projects. I'd like to see where they fall in. If they meet ASTM C309, we know where they fall in. They're under the 0.55. I don't really know where that number came from. Tried to research that. If anybody here knows, I'd love a little hint. Came up from about 1941. I know that. Right around then is when C309 came about. That's when it appeared in the publication. I just would like to know the study on how they got to that number. Is it a wear resistance? Was it a bond strength of the surface? What exactly? How did they measure and come to 0.55? Because I'm curious, what if we have 0.56 kilograms per square meter in 72 hours? Is that no longer a curing compound? It's not one that meets C309, I agree, but is that now all of a sudden ineffective? I don't think so. We have bond breakers in the market right now. Bond breakers don't usually meet C309, but they do retain moisture. They retain quite a bit. They may be at 0.65 or 0.75. Right? So bond breakers I've seen really effective at curing the concrete surface. They don't meet C309, so if C309 is specified, bond breaker's not going to do it. We're going to have to ask for the ability to use the curing compound or the bond breaker. So what about our silicates? Well, everybody would love for a silicate to work, right? Can we just put a silicate down? Well, the moisture loss for a silicate is much greater, right? I mean, there's all kinds of different ranges, but probably up in the 2 range, 1.5 to 2 kilograms per square meter in 72 hours. Is that enough? Well, we've seen issues on projects, and I'll show you some photos, So that's what a curing compound is. Do we need C309? I really don't know. If it's specified, certainly then that's a requirement for the project, but there may be other ways, and we're looking at that now, trying to do some research. One of the things, though, when you're reviewing a data sheet submittal for a curing compound, many of them say it's a hardener dust proofer, and if you look at the bold print there, and I tried to block out the product name here, I'm not trying to throw anyone under the bus, but a lot of these documents will say, meets the moisture retention of ASTM C309 on hard trowel surfaces. And I quoted that part, on hard trowel surfaces. That sounds great. We're going to do a hard trowel surface. It meets our needs. Well, what they're saying here, when they're saying it meets C309 on hard trowel surfaces, it meets the test. It meets C156 on a hard trowel surface. Now, if we take a closer look at C156, that test where you put it in that high temperature, low relative humidity, it is a concrete block, a prism of concrete, given one pass of a wood float. It is not a troweled piece of concrete. One pass of a wood float, we apply our curing compound. We're trying to see how effective the curing compound is, and we measure that. We're not measuring how effective the trowel finish is, because the harder you trowel that slab, the more you're going to lock in the moisture. So if we change that test from a wood float finish to a hard trowel finish, suddenly we don't need anything on the surface. It passes itself. It meets the 0.55 in many cases, depending on how hard you trowel that. Now, if you go to a lab, if you know how this test is run, it is not run C156. It's not run properly in most cases. It's a really difficult test. It seems easy. We'll have a curing cabinet, put it at the right high temperature, low relative humidity. Those are just simple controls. but you have to have this airflow. It's really a difficult test. Making the sample is very difficult. Troweling the sample is very difficult. How do you trowel a little prism of concrete to equal what you're getting in the field? So it's supposed to be a wood float finish. And here they're saying that they did that test and passed the test on the hard trowel prism. That's how they pass it. So I always flag that. And I'll ask for the backup data, and let's talk to the manufacturer. I want to know. I mean, I'm not rejecting the submittal, but it's curious that they said that. What I want to see is meets the moisture retention of ASTM C309, period. It meets it. Don't need to add any qualifying statement after that. That's what you're looking for. So look for that in your submittals and just ask the question. There's a lot of products out there, probably more than 75, 100 products out there that we see constantly being, just make sure you know what you're getting, because it sounds good. You read it. There it is, C309, approved. So, all right, let's talk about it. Would it be okay to put a silicate down and no C309 curing compound? This is a project I was on. Walls were up, roof was on. Look at that place. Look at the humidity in that place. It reminded me of a curing chamber in a lab. Same thing. So if you go back to that again, that's a curing room. We're placing the slab in the curing room. That's excellent curing environment. We don't need to necessarily put a cure cover down or put sprinklers or soaker hoses in there necessarily. We don't need to put a curing compound down necessarily, right? We're kind of curing that concrete. We have passive curing. So if you look in our ACI 308 guide, it talks about passive curing, right? Under conditions that prevent excessive moisture loss from the concrete, or when the required performance criteria for the concrete are not compromised by early moisture loss, it is entirely possible that no deliberate action needs to be taken to protect the concrete. Excellent. Passive curing. You don't need to do anything. Silicates would work wonderfully in that case because you don't need anything. So I'm not saying we shouldn't do it, but we have to make sure in that document it also says, note that in most environments it's unlikely that this will be the case for the entire curing period. So we have to monitor that, right? So we do a lot of work with walls, precast walls, and roof is in place. So we say, silicate here would work fine. We have to make sure that we're above 80% relative humidity, monitor that, make sure we stay above that, watch our temperatures. We're curing, we're creating a curing chamber is what we're doing. It is entirely possible, but in the winter time, what do we use? We use heat. We heat that place. We de-water it, we're taking that moisture out of the air. The relative humidity in the winter time is very low. It all froze. It's snow on the ground. It's not there, and it's not only in the northern climates. There was a project I worked on, and it was done under walls and roof. They used a silicate for the curing compound, worked wonderfully, but the problem was the insulation in the roofing became saturated and became a problem. It required replacing, actually. So on the next project, they said, you can't let my insulation get wet like that. So they brought in these big industrial dehumidifiers, and they dehumidified that building. It is no longer a curing chamber, right? Now we've got an issue. That silicate didn't work very well in that case. It worked on the first one. I don't know why it didn't. This is why. This is exactly why it didn't work. A lot of our e-commerce are using these robots. I'm sure we've all heard it. We've seen it on TV. I know when they first came out, I wasn't allowed to even look at them, couldn't take a picture of them. Very private technology. Now I think we've probably all seen these robots in these facilities. So when you order something online, it goes to the distribution center or the fulfillment center, and a robot actually goes and picks up the shelf unit and brings it to the person who puts it in the box and mails it to you. That's how it works. It's very automated, 24 hours a day, 7 days a week, 365 days a year, right? This is the robotic area of one of our facilities, and you can see the wheel paths. The robots go in very defined wheel paths, and they take about 3,000 passes per day in each of these wheel paths. They come up, they see this little symbol that's on the floor, it knows where it is, the computer system knows where it is, it spins and it goes in the other direction, on its way to go get that shelf unit and bring it back to the human who puts it in the box and mails it to you. So if you look at that, this one's 5 years old. And what we're starting to see here is some significant wear. Now, this particular project, this is on an elevated mezzanine slab in a large facility, 2.5 million square feet. The walls and the roof were in place, and in this particular one, I know that the big push was to use a silicate. We've got walls and roof. You know, can we use a silicate? Is it going to pass? Is it going to be okay? We don't have time to clean it off. They're right on our heels. They're moving in their conveyor systems, and you know, they want to test the robot system. Everything's happening at the end. We don't have time to clean off a membrane-forming curing compound. So, you know, many times a silicate is given a thumbs up and it's approved. And, you know, we just need to keep our eye on that because we're seeing this wear now. You know, and I can't tell you if we'd used a curing compound if it would have come out any better. I mean, these things are 3,000 passes a day, 7 days a week, 365 days a year, just constant. So, you know, we need to keep an eye on that. Wear resistance, abrasion resistance. How am I doing on time? Okay. So another thing I want to talk about is what happens when our bleed water goes up to the surface. In these concrete mixtures, as I said, they're optimized. We pack as much aggregate as we can into these mixtures because it's all about reducing and minimizing the paste content. So we have a lot of rock in these mixtures, and that rock ends up very close to the surface. Really important to look at gradation, finishability, and things like that because these are rocky, bony mixes. When they come down the chute, there's no way I'm going to finish that. Look how rocky it is. But if you get it right and it's optimized correctly, very finishable. You have adequate paste, and you get a really nice surface. But you do have aggregate very close to the surface. And what happens to that aggregate during the bleed process? Right? During that early age bleeding, that bleed water comes up, forms puddles on the surface, it bled to the surface, it goes around the near surface aggregates, deflected around those aggregates. So what's leaving there starts to dry out. It's the paste, those little thin mortar layers right over the aggregate starts to dry out right during the bleeding process, very early on. If we don't do anything to actively cure and hydrate those thin mortar layers, what happens later on? As they dry out, they weren't able to develop the strength, the bond strength to the aggregate below. They don't have adequate bond strength to the aggregate below. So what happens here? We're seeing a lot of this. Mortar flaking. Mortar flaking can be caused by a lack of curing. So, you know, here's an example of mortar flakes. And this is, you know, an owner doesn't want to see this. This kind of thing will interrupt a robot. And if one robot goes down, the whole system has to shut off because now we've got a robot stuck out in the field. We can't have any other robots go in. If the whole field shuts down, the whole facility shuts down, you don't get your book, you complain, it's a problem. You know, these people cannot have a robot shut down. They cannot have it. It's a challenge for us because they can't maintain their joints, they can't maintain their surface. They perform very little maintenance in these facilities. You just can't shut them down. It's like pulling teeth to even get in there and take a look at how the floor is performing. So, you know, we don't want to miss the opportunity to hydrate that near surface mortar above those aggregates. All right, what about carbonation? I'll just talk really quickly. Here's an unvented fossil fuel burning heater, right? You're putting a lot of carbon dioxide into the air. We all know what happens, the carbonation, and there's early age carbonation, giving you a weak surface, and later age carbonation. We just heard about that in the last presentation. And sometimes you result in a dusty floor, a weak surface, right? A surface where you just can't keep that surface clean. No matter what you do, you can still see that dust. It just keeps forming, right? And in this case, very often the first thing to do is to try those silicate surface hardeners. If there's calcium hydroxide there, these surface hardeners will react with that and harden it. It's certainly the first thing you can try to do. I've had pretty good success putting a silicate down on a dusting floor and solving it that way. If you don't do that, the only other way to do it is to remove that dusty, weak surface layer. So you're out there with grinders. Now we have ride-on grinders. So we put on our double trowels, we put grinding wheels on those, and we can ride. You can grind it off pretty quickly, but it's an operation. Right, but in the end, here's what we get for our concrete slabs. We can get these. Hardening, silicates, important. Curing, also very important. Two different processes. Right? The last thing I want to talk about real quick is moisture vapor. I know we had a couple questions there. I do a lot of moisture vapor investigations, and here's just a couple of failures. You don't want to see these. Think moisture vapor is part of the hydrologic cycle. We all learned about that when we were in third grade. I have a third grader, and he's learning about this hydrologic cycle, and I love it because in my seminars I talk about moisture vapor. I usually show that. We know the groundwater table evaporates moisture, and that moisture goes up to the clouds where it condenses, and then it rains back to Earth, and it goes back, and it's a process that happens everywhere on planet Earth. So I love and hate hearing people in Phoenix, it's a dry heat, and our water table's 1,000 feet down. We don't have a moisture issue. Of course you do. Wherever that water table is, moisture is evaporating from that water table, coming up through the ground, coming up through your concrete slab, right up through your building. If you've got HVAC, that takes it out. If you don't, it goes right up to the clouds. That's where it wants to go. Concrete is a good liquid water retainer. We use it for pipes, we use it for tanks, we use it for dams, but water vapor right up through concrete. Concrete doesn't retain water vapor. So how do we do this? Usually we have a moisture vapor retarder under the concrete slab. We need that. We need to stop that vapor, and that's the purpose of it. We call them retarders now. Even a plastic sheet doesn't stop the vapor. It only slows it down. Vapor goes through plastic sheets, and it goes through your slab. So the idea of a vapor retarder under your slab is to get it to go slower than whatever finished flooring you're going to put on top, so that you don't get the backup of moisture. It's going slow enough that it goes through your slab and goes through your floor covering and doesn't build up. Vapor doesn't cause a floor failure like this. It's not the vapor. It's the condensation of the vapor back to a liquid at the surface of the slab, forming a very high pH solution that breaks down our adhesives. So if we can avoid the amount of moisture that condenses to liquid water, we avoid these. Right? So when we get on a project and we notice that, oh my gosh, it's not ready, it didn't dry, now what do? We got to put a floor covering down. Can silicates be used? Because I've seen them submitted many times, and in their literature they say that they are moisture mitigation systems, some of them, not all of them. So can we do that? Well, there's a couple of standards on that. There is a standard F3010, F3010, which is the standard for moisture mitigation systems. It's relatively new. It's about 10 years old. And in that standard, it uses the same permeance as the vapor retarders. If you look at the vapor retarder spec, it says you need to have 0.1 perms. So 0.1 perms is the vapor retarder. 0.1 perms is also the mitigation system. Makes sense. How about silicates? There is no standard for that. There's no standard for a silicate, so there's nothing they have to measure to. So I always suggest we use ASTM E96, which is the test method that's used in that F3010, to measure the effectiveness of silicates. If you can show me that it does stop vapor or slows down vapor, then an integral silicate would work, or a topically applied silicate would work. We have tested them. We want that to happen. That would be a wonderful thing for the industry if one could come out. We're encouraging that. Every time we test them, we don't get that they have any impact on that vapor. They don't change the vapor emission or vapor transmission rate substantially, even measurably at all. So that's all I wanted to point out on those things. So silicates are hardeners, densifiers. I believe in them. My owner clients all want them. We want to use them, but we also need to make sure we cure the slab. And if you need a moisture mitigation system, you need to have another system too. Currently, I believe. So that's. If there are any questions, I'd love to field those.